Alright, so we're going to be taking a look at conservation of energy and momentum in collisions. And just like when we were looking at conservation of energy, conservation of momentum is a great alternative to more complex problem solving, or sometimes the only way to solve a problem more completely given some certain amounts of information. The reason that conservation of energy and momentum are so important is because forces vary during collisions. And remember, if we're going to be determining work equals force times displacement, and in that situation that force has to be a constant force, because if you have a varying force, right, then you're going to have to figure out some sort of an average area under the curve. Alright, so forces definitely vary during collisions, which is going to make them complicated to calculate directly. That means that instead of using Newton's second law, force equals mass times acceleration, and instead of using a calculation like work equals force times distance, these are the types of problems that we'd prefer to use conservation laws instead. Right, so every time we wanted to use energy instead of forces, this is the same sort of situation that we find ourselves in with momentum. So, something to consider. If we know the motion of objects before a collision, then we can determine a whole lot about the motion of the objects after a collision using conservation of momentum and energy. So this is very similar to a situation where if we know the total energy or the total mechanical energy of a process, and we know whether or not that energy is conserved, then we are able to determine a lot about the motion and the energy of that system throughout. Now we're going to be doing that same thing and using conservation of momentum and energy to do it. So when two objects collide, momentum is conserved. Remember that momentum isn't conserved indefinitely, right? The thing that must happen here is the time interval that the collision happens in is very, very small. We can consider immediately before and immediately after. But sometime after a collision, oftentimes there are other external forces that are going to end that conservation of momentum. And this only works because we say that the force of collision is so very much greater than any force that's acting externally that we can assume that it's the only force that's acting during a collision. And that's a really important assumption that we want to make. So that's what we say, that's what we're assuming when we say two objects collide and momentum is conserved for the collision. Those are the conditions that we're assuming are true. If two objects are very hard and no heat or other form of energy is produced during the collision, then the kinetic energy is also conserved. So let's think about that again. If you have two objects and they're going to collide with one another, for sure momentum is conserved. Right? That's going to be true because during the collision, the force of the collision is the greatest force. It's so much greater than any external force that we can say that it's the only force, and we're saying, yep, momentum is conserved. Now, if those two objects are very hard, which is just a physical condition that we're going to have to assume is true, and here is an actual something that we can say for sure is happening. No heat or other forms of energy are produced. So that means that we're not losing any energy from the system due to external forces. We're not losing anything from the system due to non-conservative forces. If we're not losing any energy due to non-conservative forces, and there's no other energy transformation happening, then kinetic energy is also conserved. So that means that during the collision, the initial sum of kinetic energy is going to equal the final sum of kinetic energy. Or remember, we could say that the sum of kinetic energy of the two objects before the collision is going to be equal to the sum of the kinetic energy for the two objects after the collision. That's our prime there. We say this because when two objects collide, if they're very hard and they're not going to transform their energy into any other form, for a very brief time at the moment of collision, think of those videos that you watched of the deformities that occurred. During those times, the energy is stored as elastic potential energy, which is a form of mechanical energy within the system, and then released immediately after the collision in the form of kinetic energy again. So what ends up happening is that we call this an elastic collision because it's got elastic potential energy storing and restoring the kinetic energy. So an elastic collision is a collision in which all kinetic energy is conserved. So we say that the sum of kinetic energies before would be for kinetic energy for object A, and kinetic energy for object B is going to be equal to, because that's what a conservation says, the kinetic energy of object A after the collision summed to the kinetic energy of object B after the collision. So what we're saying here is that the individual kinetic energies aren't necessarily identical, but the sum of those kinetic energies is going to be a conserved quantity. That's a really useful strategy to know that occurs during any collision which we would call an elastic collision. All kinetic energy is conserved, and it's conserved because it was stored very temporarily at the moment of collision as elastic potential energy and then restored or sent back via a mechanical pathway into kinetic energy into the two objects. A few things to know is, first, this is true for all atomic level collisions. So if you've got a proton and a neutron colliding with one another, two electrons colliding with another, two atoms in a collision, these collisions occur and they are elastic. So we could say that at the atomic level we only experience elastic collisions and kinetic energy is conserved. However, in the real world and on the macro scale, so at the big people sizes, you almost never get a perfect elastic collision. But what we do is we say that things like billiard balls come close, and so a lot of times when you have something that comes very close to the ideal collisions of an elastic collision, we'll say assume that the collision is elastic and assume that the kinetic energy was conserved, and then we'll be able to approximate very accurate values. So even though it's never completely true at a macro scale, sometimes we will assume that a perfectly elastic collision will come close to giving us the true values. Now, something to remember, we said that at the macro scale, kinetic energy is not always conserved. Almost always you have some energy lost due to heat or light or sound or some other energy transformation. But even if it's not conserved, even if kinetic energy is not conserved in a collision, the total energy is still conserved, because that's a law in physics. That's a law in the universe that is always true, and it will always hold true, that energy in total is conserved. It's just a matter of whether it's conserved within the system or conserved externally. It leaves the system, but it's still there. It's still a matter of if it's conserved as kinetic energy or if it's conserved as some form of potential energy. But only elastic collisions have a total energy conserved that is kinetic. So that means that all other types of collisions we're going to call inelastic. So an inelastic collision is when kinetic energy is not conserved and it's lost to some of that energy is lost to the surroundings. So the total energy is still conserved, but some of it has been transformed into other forms. Some other forms that are very common in collisions, in fact the most common energy transformation in a collision is thermal energy. You will also experience some energy loss due to sound, light, and other types of energies. But remember, the total energy is always conserved. It's just a matter of whether it's conserved within the system and what form the energy is conserved in. So that means that for inelastic collisions, the initial kinetic energy, sum, is going to be equal to the final kinetic energy, sum, plus the other forms of energy, which we could represent by the work done by non-conservative forces or just other forms of energy. And that will be true for inelastic collisions. So let's take a look at, we said that billiard balls come pretty close to a perfectly elastic collision. So we're going to first take a look at the situation where you get two billiard balls, and those two billiard balls have a perfectly elastic collision. So we're going to assume that the mass of billiard ball A is equal to the mass of billiard ball B. And if that collision is elastic, then that means that at the moment of collision, you temporarily get all of your energy is stored in the form of elastic potential energy. And then it's restored to the objects in the form of kinetic energy, so that the sum of kinetic energy is equal to the sum of kinetic energy before the collision. So that's true for objects that are experiencing an elastic collision. If the collision is not elastic or partially not elastic, then the total energy might in part be stored as elastic potential energy, but also it will be transformed to other forms. And so that means that in that situation, the velocities after will actually be less than the total kinetic energy before the collision. And that's happening in an inelastic collision. So the two objects approach each other with equal speeds in this situation. We're going to assume that VA equals VB. When they bounce off with equal speeds in the opposite direction, so that means that if the masses are the same, then their velocities will be the same after the collision. Note that the direction changed. So that means that VA prime will equal VB prime as far as magnitude goes. However, if the collision is inelastic, they'll bounce back a lot less or not at all for an inelastic collision. So that means that VA prime won't equal VA initially in magnitude, and these are going to be a much smaller value to give us the less kinetic energy. So we're going to be taking a look specifically at how to problem solve for both elastic and inelastic collisions. And we're going to make sure that we know the rules and how to apply conservation of momentum and conservation of energy to do this problem solving.